So in this video, we're going to talk about how to determine the inverse of a function with domain restrictions. So sometimes when you find the inverse algebraically and graph the new equation, you'll notice that the graph is not a function. And you can tell that it's not a function because it doesn't pass the vertical line test. Remember that if any vertical line passes through a graph more than once, then it is not a function. So you can see that in a function, it doesn't matter how many vertical lines you draw, they'll all pass through the graph only once. Remember that this is another way of looking for repeated x values in the domain. So remember that the set of all inputs or x values in a relation is called the domain. The set of all outputs or y values in a relation is called the range. And remember we discussed the different ways to represent the domain and range. We can use inequality, set builder notation, or interval notation. So remember, to find the inverse from an equation, we're going to start off by replacing f of x with y, and then we're going to switch our x and y. Then we're going to solve for y using the inverse operations that we discussed and work on isolating y. If the inverse is a function, remember that we'll use inverse function notation, which looks like this, to represent the equation. So let's start off by finding the inverse of f of x equals x squared and then graph the function and its inverse. So let's go through the steps like we discussed in the previous video. So what I'm going to start doing is I'm going to replace f of x with y. So I get y equals x squared. And now I'm going to switch my x and y. So that gives me x equals y squared. And so now what I need to do is undo this squared in order to solve for y. Well, remember that anytime we have a power, we can undo it using the root. So since I have a squared power, I'm going to undo it using the square root. So I'm going to take the square root of both sides of my equation. And when I do that, that's going to give me plus or minus the square root of x equals y. So now let's graph the function and its inverse. Well, here I have the graph of the function and its inverse, right? You can see here in purple, I have the original function, and in green, I have the inverse. Well, notice that the inverse does not pass the vertical line test, right? So you can see all of these vertical lines are passing through this graph more than once, so it is not a function. So here's an issue that we come across. So how do we know when the inverse of a function will not be a function? Why does it happen? And what are we going to do now? So here's the answer to the first question. How can we know when the inverse of a function is not going to be a function? Well, this situation happens when f of x is not a one-to-one function. Okay, and that's the situation we have with f of x equals x squared. In a one-to-one function, every input in the domain has a different value in the range corresponding to it. So basically what that means is that no y value is repeated. Okay, and that's something that we haven't really talked about because remember, when we're trying to determine if something is a function, we say, okay, well, look at x, and if no x is repeated, then it is a function, right? But if no y values are repeated, then we say the function is one-to-one. Okay, so you can see here we have y equals x and y equals x squared. Okay, and I have the tables for both of these functions. So they're both functions, right? Because we don't have any repeated x values. However, y equals x is a one-to-one function because if you look at the y values, they're all different. Y equals x squared is not one-to-one because look at all these repeated y values, right? Like the 9 is repeated, the 4 is repeated, 1 is repeated. And if we keep looking at this table, you'll see that there's a lot of repeated y values. So y equals x squared is not a one-to-one function. So that's why when we find the inverse, we notice that the inverse is not a function. Because think about it, when we're finding the inverse, we're switching x and y, right? So the domain of the original becomes the range of the inverse. The range of the original function becomes the domain of the inverse, okay? Well, if I take this y value, right? If I take all my values in the range and make them my new domain, well, these repeated y values are going to become repeated x values. Okay, so that's what makes the inverse not a function. It's those repeated y values becoming repeated x values. Now, how do we fix this problem and make sure that our inverse is a function? Well, what we can do is we can create something called a domain restriction on the original function to make it one-to-one. So we're going to limit the values of x that we include to make sure that there are no repeated y values. So let's figure out how to restrict the domain of f of x equals x squared to ensure that the inverse is a function. So what we do is we're going to take the graph of f of x equals x squared and cut it in half. So we can do this for a quadratic by taking the part of the function that's being squared, setting it greater than or equal to 0, and solving for x. So we know that, for example, in this function, the part that's being squared is x, right? So we would just say x is greater than or equal to 0, and we're going to restrict the domain that way. Well, notice what happens when we do this is we create a one-to-one function, right? Because we're only taking one half of the y values, so that's going to be a one-to-one function. So now when we figure out the inverse, well, we have f of x equals x squared, right? Which gives us y equals x squared. And then when we switch x and y, we get x equals y squared. And now we can take the square root of both sides, which gives us the square root of x equals y. Okay, and so this square root is the principal square root, right? So that's just the positive square root. And so that's all we need to get the inverse of this function. So now this function has been made one-to-one using a domain restriction. And so if I graph this now inverse that I found, right, the square root of x, notice that it is a function, right? You can see that it is passing the vertical line test. And if we look at our x and y values, notice that I did switch my x and y, right? So the inverse is correct. It represents a reversing of x and y, and it is a function. So notice that, this is a fun fact. Notice that the inverse of the quadratic parent function, which is f of x equals x squared, is actually the square root parent function, right? So that square root of x is on the list of our parent functions, and that is the square root parent function. So let's put this all together and work on finding the inverse from an equation now that we know about domain restrictions. So before we go ahead and start finding the inverse algebraically, we need to first determine whether the original function is one-to-one. Okay, so if it is not one-to-one, we need to do a domain restriction to make it, to make sure that when we find the inverse, we're finding a function. So for quadratic functions, we're going to do this by setting the part of the equation that's being squared greater than or equal to 0 and then solving for x. Then we're going to go through our algebraic steps, right? Replace f of x with y, switch x and y, and then solve for y using our inverse operations. So now we'll have an inverse that's a function, so we can use inverse function notation to represent it. So let's try finding the inverse of f of x equals x squared plus 1. And then we're going to graph the function and its inverse and then describe the domain and range using any restrictions. So step 1, what we're going to do is determine whether the original function f of x is one-to-one. The best way to do this is to go to your calculator. Okay. You can write out all the table of values if you want to, but I think it's a little bit quicker if you go to your calculator and type x squared plus 1. Then if I click second table, and if I scroll through my table of values, you can see here I have these repeated y values, right? You see I have this 10 repeated, 5 repeats, 2 repeats. So I know that this is not a one-to-one function, okay? So I know I'm going to have to go ahead and restrict the domain. So to restrict the domain, I'm just going to look at the part that's being squared. Okay, so in this function, the part that's being squared is x. So I'm just going to say x is greater than or equal to 0. Okay, that's my domain restriction. So that's the restriction I'm going to put on this function so that I can ensure that my inverse is a function. Well, then the steps after we do this are just the same that what we've been doing, right? So we're going to replace f of x with y. So I'm going to have y equals x squared plus 1, right? And then I'm going to switch my x and y. So when I switch x and y, that gives me x equals y squared plus 1. And now I'm going to solve for y. Remember, when I solve for y, I need to work my way from the outside in, right? So I'm going to start off with this minus 1 to get rid of my plus 1. So I have x minus 1 equals y squared. And then now I'm going to take the square root of both sides. And when I do that, I get the square root of x minus 1 equals y. So now let's graph our original function and our inverse and make sure that our inverse is a function. So let's look at this. So our original function, notice that we restricted it so that x is greater than or equal to 0. So we'll say that the domain is going to be from 0 to positive infinity. And that's going to make the range. Well, notice the starting value of the range is 1. So the range is going to go from 1 to positive infinity. And then now let's look at our inverse. So notice it does pass the vertical line test. We can see that by these grid lines on Desmos. And so the domain is going to go from 1 to positive infinity. And notice that the range is going to go from 0 to positive infinity. Okay, and notice that this does hold that relationship, right? You see how the domain and range have been switched when we go from the original to the inverse, okay? So we can now say that this inverse is a function, and we can represent it using inverse function notation. So let's try another example. Let's try finding the inverse of f of x equals x plus 2 squared. So remember, the first step is going to be to go to our calculator and go ahead and try to figure out if this is a one-to-one function. So I type x plus 2 and then close parentheses and then squared. And so now I'm going to go second table and I'm going to look at my table of values. Well, notice that if I scroll up in my table of values, I can see that I have a bunch of repeated y values, right? So this is not a one-to-one function, so we need to restrict the domain. So remember, the strategy to restricting the domain is to take the part of the function that's being squared and then set it greater than or equal to 0 and solve for x. So I'm going to say x plus 2 is greater than or equal to 0, and then I'm going to solve this inequality for x. So I can do that by subtracting 2 from both sides, and when I subtract 2 from both sides, I get x is greater than or equal to negative 2. So that's how I'm going to restrict the domain of this function. So what I'm going to do now is I'm going to find the inverse. So to find the inverse, I'm going to replace f of x with y. So I have y equals x plus 2 squared. Now I'm going to switch my x and y. So I have x equals y plus 2 squared. So to solve this for y, remember I need to work my way from the outside in. So I need to start off by taking the square root of both sides so that I can undo that squared. So I have the square root of x equals, and then that squared and squared cancel each other out, so I have y plus 2. Now I need to subtract 2 from both sides, but remember that minus 2 is going to stay outside the square root, right? Because I took the square root and then I subtracted 2. So this is going to become the square root of x minus 2 equals y. So now I'm going to graph this function and this inverse and see if the inverse is a function. So when I do this, you can see that my inverse does pass the vertical line test and it is a function. Okay, so now let's describe the domain and range. So since I restricted the original function, the domain values are going to be from negative 2 to positive infinity. And that's going to make the range go from 0 to positive infinity, right? I'm getting these values from my graph. So now for my inverse function, I can see that the domain values, they start at 0 and they go to positive infinity. And then my range is going to go from negative 2 to positive infinity. Okay, and since my inverse does pass the vertical line test, I can write it at using inverse function notation, right? So f inverse of x equals the square root of x minus 2. So now let's try this example. Let's try finding the inverse of f of x equals x cubed. So this is a cubic function, right? It's a little bit different than our quadratics. So first we're going to see and figure out if this original function is one-to-one. So I'm going to go to my calculator and I'm going to type x cubed. Okay. And when I look at my table of values, notice that this function does not have any repeated y values, right? You can keep scrolling forever in the negative direction or forever in the positive direction, but you're not going to see any repeated y values. So this is a one-to-one function, so I don't have to worry about domain restrictions. So all I need to do now is the steps we were doing in the previous video, and I need to go ahead and, switch f of x with y. So I have y equals x cubed. And then I'm going to switch my x and y. So I have x equals y cubed. And so now I need to solve this equation for y. Okay. Well, remember, inverse operations tell us anytime you have a power, you can undo it with a root. So this is a cubic power. So I'm going to undo it with a cube root. Okay. So I'm going to take the cube root of both sides of my equation. And when I do that, my y cubed and the cube root are going to cancel each other out. So I have the cube root of x equals y. Okay. And this should be a function, right? Because I didn't need to restrict any of my domain. And you can see that, in fact, it is a function, right? So everything does pass the vertical line test. So my original function, it has a domain. Notice that it goes on forever. So the domain is going to be from negative infinity to positive infinity, and same idea with the range. Okay. And then my inverse also does go on forever in both directions. So it's going to be negative infinity to positive infinity. And the range is also going to be negative infinity to positive infinity. So we're going to continue our study of inverses as we learn about different types of functions throughout this year. So you will see this coming back in a lot of our units, right? This idea of finding the inverse, and then sometimes we'll have to restrict the domain, sometimes we won't. And then when you'll see this, you'll see that there are general patterns to the types of functions that we talk about and their inverses. So the inverse of a linear function will always be another linear function. Okay. The of a quadratic function will always be some type of square root function. The inverse of a cubic function will always be some kind of a cube root function. The inverse of a rational function is always another rational function, and the inverse of an exponential is also always going to be a logarithmic. And this also works in the reverse direction. So, like the inverse of a square root will be a quadratic, the inverse of a cube root will be cubic, the inverse of a logarithmic function will be exponential. So before finding the inverse of a function, you need to first check whether it is a one-to-one function. If it is not a one-to-one function, then you need to first restrict the domain before finding the inverse in order to make sure that the inverse is a function.